On a clear night, far from any city, you can look up and see a pale band of light stretched across the sky. That band is the Milky Way, seen edge-on from the inside. It is our own galaxy, 100,000 light-years wide, holding a few 100 billion stars. It looks close enough to touch. It is not. We have sent machines beyond the planets, and the fastest of them, after almost 50 years of flight, has not yet crossed even 100th of the way to the nearest star. Tonight the question is simple to ask and strange to sit with. Could a human being ever leave this galaxy, not just our solar system, but the whole bright wheel of it? The honest answer is that the galaxy holds us with a grip far stronger than distance alone, and the reasons reach deeper than rockets. Let's follow them, slowly, one at a time. Go outside on a moonless night, far from any streetlight, and give your eyes about 20 minutes to adjust. A faint river of light will slowly rise into view, arching from one horizon to the other. People have watched it for as long as there have been people. The Romans called it the Road of Milk. The Greeks called it Galaxias, the Milky Circle, and that one word became our word for an entire class of objects in the cosmos. We named the largest structure we belong to after the way it looks on a dark night. For most of human history, nobody knew what the band was made of. It looked like spilled light, like a low mist that never cleared. Then, in the winter of 1610, Galileo Galilei turned his small new telescope toward it and watched the mist break apart into separate points. The pale glow was stars. Not a few, not hundreds, but more than he could count, packed so thickly and lying so far away that the naked eye smeared them into a single wash of light. That wash is our home galaxy seen from the inside. We live within a vast flattened disk of stars, and when we look along the plane of that disk, we are looking the long way through it. The light of hundreds of billions of distant suns piles up into one band. When we turn instead toward the empty space above or below the disk, we see far fewer stars, and the sky goes dark. The shape of the night sky is really the shape of the thing we live in. Look closely and the band is not smooth. Dark rifts cut through it, like tears in a sheet of light. Those lanes are not gaps where stars are missing. They are clouds of cold dust and gas drifting between us and the stars behind them, soaking up the light. The dust is finer than smoke, but there is so much of it spread across so many trillions of kilometers that it lays shadows across the whole galaxy. That same dust is the raw stuff from which new stars and planets are still being made. The brightest, most crowded stretch of the band sits in the direction of the constellation Sagittarius. When you look that way, you are looking toward the center of the galaxy, toward the dense core where stars swarm in their millions and an enormous black hole waits. That center will matter later for the question we're asking tonight. When you look the other way, toward the constellation Auriga, you're gazing outward, toward the thinning edge. Hold a simple picture. Think of a dinner plate made of light, with a swollen yolk at its middle, turning slowly in the dark. You're a single speck set into that plate, well out from the center. From inside it, edge on, the rest of the plate wraps your sky as a glowing band. That band measures roughly 100,000 light-years across. The number is easy to say, and almost impossible to feel, and making it feelable is much of what these next 2 hours are for. The Milky Way looks close enough to wade into. It looks like something a person could leave behind given a fast enough ship. The truth runs the other way, and to see why, we first need to find out exactly where in this great wheel of stars we happen to be standing. Start with our street address, and the galaxy stops feeling like a backdrop and starts feeling like a place. The Sun sits about 26,000 light-years from the galactic center. That is roughly 2/3 of the way out toward the edge, in the quiet suburbs rather than the crowded downtown. We are not at the heart of anything. We are far out on the rim, in a calm and unremarkable patch, which is part of why life had the steady conditions it needed. We live inside a minor spiral feature called the Orion Arm. Astronomers also call it the local arm or the Orion spur, and the name comes from the constellation Orion, whose bright stars sit along it as we see them. The galaxy's grand spiral arms are the Sagittarius arm, lying inward toward the centre, and the Perseus arm, lying outward toward the rim. Our Orion arm is a smaller bridge of stars and gas tucked between those two larger ones. We do not live on a main boulevard. We live on a side street between them. The whole arrangement is turning. Our entire neighbourhood orbits the galactic centre, dragging the sun and every planet around with it. We're moving fast by any human measure, something like 230 kilometres every second, faster than any rocket we have ever built. Yet the distance is so enormous that one full lap takes roughly 230 million years. Astronomers call that single circuit a galactic year. Sit with that figure for a moment. The last time the Sun was at this exact point in its orbit, the first dinosaurs were just appearing on a younger Earth. Every dinosaur that ever lived, the long age of their rule and their sudden end, the rise of mammals, the whole story of the apes, the brief flicker of recorded human history, all of it has unfolded inside a single galactic year. The galaxy turns so slowly that no civilization could ever watch it move. The motion is real, steady, and far beyond the reach of any one life. There is something steadying in knowing the address. We are not falling through random emptiness. We are riding a slow, fixed orbit around a definite centre on a particular arm at a measured distance. The Sun has made this circuit roughly 20 times since it first lit up. It will make many more before it dies. The address also frames the journey ahead. If a ship ever set out to leave the galaxy, it would not be starting from the middle, where escape might at least be a short, straight line outward. It would be starting from here, deep on the rim, with 26,000 light-years of stars on one side and the thinning edge on the other. The question of leaving the Milky Way is, before anything else, a question of leaving from a very particular and very deep place inside it. To understand how deep, we need to see the full shape of the structure we are embedded in, not just our spot on the rim. The band overhead is only the part we can see edge on. The galaxy has a thickness, a swollen middle, and a faint surrounding shell that reaches much further than the bright disk suggests. That hidden shape is the next thing to map, because the real walls around us are not only made of distance. Lift the galaxy out of the night sky and turn it in your hands and three parts come into view. The first is the disk, the flat plate of light we live inside. It stretches about 100,000 light-years across and runs only about 1,000 light-years thick. If you shrank the whole disk to the width of a dinner plate, it would be thinner than the plate itself, more like 2 stacked sheets of paper. The Milky Way is mostly a broad, shallow wafer of stars. The disk is where almost everything familiar lives. The Sun, the bright stars of the constellations, the dust lanes, the gas clouds, the regions where new stars ignite, all of it sits in this thin layer. The disk also carries the spiral arms, the great sweeping lanes of brighter, younger stars that give the galaxy its pinwheel look from above. We never see that pinwheel from where we stand, because we are buried inside one of its sheets. At the centre sits the second part, the bulge. Picture the yolk in the middle of the plate, a dense swarm of older stars packed into a rounded core. Running straight through that core is a long bar of stars, which makes the Milky Way a barred spiral rather than a simple pinwheel. The bar funnels gas inward toward the very centre, where a supermassive black hole holds the whole structure's heart. The third part is the hardest to see, and the largest of all. Surrounding the disk and bulge is the halo, a vast and faint sphere reaching far beyond the bright edge of the disk. The halo holds the galaxy's oldest stars, gathered into tight globular clusters, ancient balls of hundreds of thousands of suns that formed when the galaxy was young. Some of these clusters orbit tens of thousands of light-years out, well above and below the disk, in regions where the night would hold almost no nearby stars at all. The halo matters more than its dimness suggests. Most of the galaxy's true bulk does not lie in the bright disk we admire. It lies spread through this enormous outer shell, in a form we cannot see directly, which we will come to in time. For now, hold the idea that the galaxy is far bigger and far heavier than the glowing band lets on. The light is only the inner part of something much larger. This shape decides what leaving would mean. From inside the thin disk, the shortest way out is not across the 100,000 light-years of the plate. It is straight up perpendicular to the disk, through that 1,000 light-year thickness and out the top. In one direction the galaxy is a marathon, in the other it is merely very far. That difference will matter greatly when we ask which way an escaping ship should point. But even the short way out, straight up through the disk, runs far longer than any distance a human craft has ever crossed. 1,000 light-years sounds modest next to 100,000. It is still a wall taller than anything we can presently imagine climbing. Before we can feel that wall, we need a single nearby yardstick, one real destination close enough to measure against. The nearest stars give us that yardstick, and they are already much further than they look. Point a telescope at the constellation Centaurus in the southern sky, and you can find the closest stars to our own. The brightest is Alpha Centauri, which to the eye looks like a single point but is really a pair of sun-like stars circling each other, named Alpha Centauri A and Alpha Centauri B. Orbiting the pair from much farther out is a small dim red star called Proxima Centauri. Proxima is the nearest star to the Sun, and the word Proxima simply means nearest. It is the closest other sun we have. Proxima Centauri lies about 4¼ light-years away. Alpha Centauri A and B sit a touch farther, about 4⅓ light-years out. These are our next-door neighbours, the very first stops any journey beyond the Sun would aim for. And here the gentle trap of the night sky tightens, because 4 light-years sounds almost cosy. It is not. A light-year is the distance light travels in 1 year, and light is the fastest thing there is. In 1 second, light crosses about 300,000 kilometres, enough to circle the Earth more than 7 times before you finish saying the word. Let that speed run for a full year, and the distance it covers comes to roughly 9.5 trillion kilometres. Write that number out and it has 12 zeros after the 9. Now multiply it. Proxima Centauri is more than 4 of those light-years away, which is something near 40 trillion kilometres. To make that picturable, shrink the Sun down to the size of a single grain of sand. On that scale, the Earth would be an invisible mote sitting a few centimetres away, and Proxima Centauri, the very nearest star, would be another grain of sand roughly 40 kilometres off, with nothing but empty space in between. The stars are not crowded. They are grains of sand scattered across whole cities of darkness. In 2016, astronomers found a planet circling Proxima Centauri, named Proxima b, sitting in the zone where liquid water could in principle exist. So the nearest star is not just a point of light. It holds a world, possibly a rocky one, the closest other ground we know of. If humanity ever reaches for another planet around another sun, this is the most likely first target simply because it is the least far. Least far still means 40 trillion kilometres, and 4 light-years, remember, is the closest case. Spread your gaze across the night sky, and most visible stars lie hundreds or thousands of light-years off. The galaxy as a whole runs 100,000 light-years wide. The nearest star is a single step, and even that single step dwarfs everything our species has ever crossed. So the honest yardstick is set. The shortest possible interstellar trip is about 4 light-years, and a light-year is 9.5 trillion kilometres of nothing. The next question is the obvious one, the one a curious person asks straight away. How far have we actually gone? We have been launching machines into space for decades. The fastest of them has been flying for nearly half a century. Measured against 4 light-years, the answer is humbling, and it sets the true scale of the gap. The fastest objects humanity has ever launched are already out there, flying right now, and their speeds tell us exactly how small our reach still is. Start with Voyager 1, launched in 1977, and still the most distant human-made object ever made. It is now more than 24 billion kilometres from Earth, so far that its radio signal, travelling at the speed of light, takes most of a day to reach us. Nothing we have built has gone deeper into the dark. Voyager 1 is moving away from the Sun at about 17 kilometres every second. That is roughly 61,000 kilometres an hour, fast enough to cross the United States in about 5 minutes. No human passenger has ever travelled anything close to that speed. By every standard of our own history, Voyager 1 is blisteringly fast, and it has been falling outward without pause for nearly 50 years. Now aim it at the nearest star and the picture changes. Voyager 1 is not actually headed toward Proxima Centauri, but suppose it were. At 17 kilometres a second, the trip to that nearest sun, 4¼ light years off, would take about 70,000 years. 70,000 years ago, our ancestors had not yet painted the cave walls of Europe. A journey begun by the earliest modern humans at Voyager's record pace would only now be arriving at the closest star. There is a faster machine, but its speed is borrowed in a way that does not help us escape. The Parker Solar Probe, launched in 2018, was built to dive again and again toward the Sun. On its closest passes, it has reached about 690,000 kilometres an hour, roughly 190 kilometres each second, which makes it the fastest object people have ever made. But that blazing speed comes from falling deep into the Sun's gravity, like a stone dropped down a well, and the probe loops right back out again. It is not leaving, it is circling. The honest measure of our reach is the outbound one, and there Voyager sets the record at 17 kilometres a second. Hold both numbers together. The nearest star is 40 trillion kilometres away. Our fastest departing craft, after half a century of flight, has covered less than 1,000th of that distance. Voyager 1 has not yet crossed even 100th of the way to Proxima Centauri. It has barely cleared the Sun's own backyard. This is the gap the rest of the script lives inside. It is not that we lack a fast machine. By the standards of life on Earth, Voyager is astonishingly quick. It is that the distances are built on a different scale entirely, a scale where our best speeds barely register. The void is not a little too big for us. It is enormously, structurally too big, by factors of thousands, and we have not even reached the hard part. So far we have only compared our top speed to one nearby star. We have not yet asked what it takes to break free of each gravitational hold along the way, the layered grips that a ship must escape one after another. The first of those holds is the smallest, the one we cleared decades ago, the pull of the Earth beneath our feet. It is worth seeing clearly, because it is the only wall on this whole journey we have already climbed. Throw a ball into the air and it comes back down. Throw it harder and it goes higher, but it still returns. There is a speed, though, at which a thrown object would never come back at all, where it would keep rising until the Earth's pull faded behind it. That speed is called escape velocity, and for our planet it is about 11 kilometres every second. Reach it, point it upward, and you are free of the Earth. 11 kilometres a second is roughly 40,000 kilometres an hour, or about 25,000 miles an hour. It is hard to grasp until you compare it. A rifle bullet leaves the barrel at under 1 kilometre a second. To escape the Earth, you must move more than 10 times faster than a bullet, and keep that speed as you tear up through the thickest part of the atmosphere. That is the wall every rocket climbs at launch. This is why a rocket on the pad is mostly fuel. The tall, slender body you see is largely a set of tanks, and the actual payload, the capsule or satellite at the very top, is a small fraction of the whole. Most of the machine exists only to burn furiously enough to reach 11 kilometres a second before the propellant runs out. The roar and the fire and the towering size are all in service of clearing this first lowest wall, and we do clear it, routinely. Since the first satellites of the 1950s, we have crossed Earth's escape velocity thousands of times. Every probe sent to another planet, every lander, every deep space mission has beaten this wall. By now it is ordinary engineering. The 11 km per second barrier, which would have seemed impossible a few lifetimes ago, is something we step over many times a year without a second thought. It helps to feel why escape velocity exists at all. gravity never truly switches off. The Earth's pull reaches outward forever, growing weaker with distance but never reaching zero. To escape, an object does not fly to some edge where gravity stops. It instead carries enough speed at the start to keep climbing against that fading pull for the rest of time, slowing forever but never quite halting and falling back. Escape is not about reaching a wall. It is about having enough motion to outrun a grip that never fully lets go. That idea will return again and again tonight, because the galaxy works the same way, only far more strongly. Each gravitational hold has its own escape velocity, its own speed you must carry to break loose. The Earth's is the gentlest of them. We cleared it decades ago, and it now feels small precisely because we mastered it. But clearing the Earth is not the same as being free in space. A rocket that reaches 11 kilometers a second escapes the planet, yet it finds itself still firmly held by something far larger and far stronger. It is still in orbit around the Sun, still bound to a star whose grip dwarfs the Earth's. We have climbed off the planet only to find ourselves standing at the bottom of a much deeper well. The next wall is the Sun's, and it is nearly 4 times as high. Escaping the Earth wins you a smaller prize than it seems, because the planet you left is itself trapped, circling a far greater mass. The Sun holds more than 99% of all the matter in the solar system. Every planet, every moon, every comet and grain of dust is a minor scrap orbiting one dominant star. Break free of the Earth, and you're still falling around the Sun, like a person who climbs out of a rowboat only to find the boat is adrift in a vast and powerful river. This Sun's grip is much stronger than the Earth's. To escape the Sun from the distance where Earth orbits, an object needs to be moving at about 42 kilometers every second relative to the Sun. Compare that to the 11 kilometers a second that frees you from the planet. The star's wall is nearly 4 times higher, and overcoming it is far harder. The Earth itself helps a little, since it already carries us around the Sun at about 30 kilometers a second, and a clever launch can borrow some of that motion. Even so, leaving the Sun behind takes a real and deliberate push. The Sun's reach is not only gravitational, the star also blows a constant stream of charged particles outward in every direction, a thin wind of broken atoms moving at hundreds of kilometers a second. This solar wind sweeps out into space and carves a great bubble around the whole system, a region where the Sun's breath holds sway against the gas drifting between the stars. That bubble is called the heliosphere, and it is, in a real sense, the Sun's own territory. The edge of that bubble is a place we have actually reached. It is called the heliopause, the boundary where the solar wind finally grows too weak to push back the gas of interstellar space. In 2012, after 35 years of flight, Voyager 1 crossed it, and its instruments recorded the moment the Sun's wind fell away and the colder gas between the stars took over. Voyager 2 crossed the same boundary in 2018 in a different direction. For the first time, human machines had passed beyond the Sun's wind and into true interstellar space. That crossing is worth pausing on, because it is often called the edge of the solar system, and in one sense it is. The Voyagers are now outside the bubble the Sun inflates. The solar wind no longer reaches them. By the measure of the Sun's breath, they have left. But by the measure of the Sun's gravity, they have barely begun. The heliopause sits about 18 billion kilometers out, which is far, yet the Sun's pull reaches enormously farther than its wind does. There is a vast region beyond the heliopause where the solar wind is gone, but the Sun still rules by gravity, still holding a great cloud of frozen bodies in slow orbit. The Voyagers have left the Sun's atmosphere, but not the Sun's domain. The true gravitational edge of the solar system lies thousands of times farther out, in a faint shell most people have never pictured. That shell is the real boundary, and it is nearly a light year deep. Far beyond the planets, far beyond the heliopause where the solar wind dies, there is a region the Voyagers will not leave for tens of thousands of years. It is a vast, sparse shell of frozen bodies wrapped all the way around the Sun, called the Oort cloud. It is named for the Dutch astronomer Jan Oort, who proposed it in 1950 to explain where certain comets come from. The Oort cloud is the true outer edge of the solar system, the place where the sun's gravity finally loses its hold. The cloud is made of countless icy lumps, the leftover crumbs from the solar system's birth, each a mountain of frozen gas and dust drifting in the deep cold. They orbit so far out and so slowly that a single lap around the sun can take millions of years. Now and then one is nudged inward, falls the long way toward the sun, warms, and grows a glowing tail. The long-period comets that visit our skies once and then vanish for ages come from this distant shell. The numbers are staggering. The inner edge of the Oort cloud may lie a few thousand times farther from the sun than the Earth does. The outer edge may reach out to something like a light year, or even farther, nearly a quarter of the way to Proxima Centauri. The solar system, measured honestly, is not the neat band of planets in a diagram. It is a sphere of the sun's influence almost 2 light years across, with the planets a tiny bright knot at its very centre. This is where the scale of leaving truly lands. To exit the solar system in full, a ship must cross not just to the planets, not just to the heliopause, but all the way through the Oort cloud and out the far side. Voyager 1, our fastest outbound craft, will not even reach the inner edge of this shell for about 300 years. It will not pass beyond the outer edge for something like 30,000 years. Our most distant machine has decades behind it, and tens of thousands of years still to go before it has merely left home. And once it does leave, it arrives nowhere. Pass through the Oort cloud and you're not at another star. You're in the open gulf between the stars, with Proxima Centauri still light years off. The Oort cloud is not a doorway to the next sun. It is only the last faint trace of our own, the outermost wisp of the sun's long reach, beyond which there is darkness for a very long way. So the layered grips come into focus. First the Earth, cleared in minutes by a rocket. Then the sun's wind, crossed by the Voyagers after decades. Then the sun's gravity, holding a shell nearly a light year deep that takes 30,000 years to traverse. Each hold is larger than the last, and we have only truly escaped the first. There is a reason we cannot simply build a bigger rocket and power straight through all of this. The trouble is not only the distance, it lies in the very way rockets work, in a hard piece of arithmetic that has shaped every launch ever made. Carrying fuel, it turns out, is a trap that tightens the more fuel you carry. To see why no chemical rocket can ever reach the stars, we have to look at the equation that governs them all. A rocket works by throwing mass backward to push itself forward. It carries fuel, burns it, and flings the exhaust out behind at high speed, and the ship recoils ahead. To go faster, it must throw more mass, which means carrying more fuel. And here lies the trap, because that extra fuel has weight of its own, and the rocket must then carry the fuel needed to move the fuel. The problem feeds on itself. This is captured in a piece of arithmetic worked out by the Russian schoolteacher Konstantin Tsiolkovsky, published in 1903, long before any rocket flew. It is called the rocket equation, and it links how fast a ship can finally go to how much of its starting weight was fuel. The cruel part is the shape of the relationship. To go a little faster, you do not need a little more fuel. You need to multiply your fuel, again and again, and the requirement climbs without mercy. A simple way to feel it. Suppose a certain amount of fuel can bring your ship up to the speed of its own exhaust. To reach twice that speed, you do not need twice the fuel. You need roughly 7 times as much. To reach 3 times the exhaust speed, you need around 20 times as much. To reach 4 times, around 50 times. Each step up in speed demands a wild leap in fuel, and the fuel you add mostly serves to carry the rest of the fuel. This is why a rocket on the launch pad is almost entirely propellant. A vehicle the height of a building may deliver a payload no larger than a bus, because nearly everything below is tanks. We push this design to its limit just to lift a small capsule off the Earth and send it toward another planet. The chemical rocket, our finest and most reliable spacefaring tool, is already straining at the edge of what its own equation allows. Now ask it to reach another star. Chemical fuel can push exhaust out at only a few kilometers a second. To cross to Proxima Centauri in any reasonable time, a ship would need to travel at a sizable fraction of the speed of light, thousands of times faster than that exhaust. Feed those numbers into the rocket equation, and the fuel required does not just grow large. It grows beyond all sense, more propellant than exists in the entire solar system, more than could ever be gathered or burned. The arithmetic does not say it would be hard. It says it cannot be done this way. This is the first deep wall that is not made of distance. Even if we had unlimited patience for a journey of tens of thousands of years, we could not build a chemical rocket fast enough to begin it well, because the fuel needed to reach starflight speeds outruns any ship that could hold it. The very method that lifted us off the Earth fails completely at interstellar scale. The rocket equation forces a hard choice. Either find a way to push exhaust out vastly faster, using something far more potent than chemical fire, or give up on speed and accept a journey measured in many human lifetimes. Both roads lead somewhere harsh. We will follow the search for faster engines later. First, it is worth facing the slow road honestly, the one where we keep our ordinary speeds and simply accept how long the crossing takes. Measured in lifetimes, that gulf is its own kind of wall. Set aside the dream of going faster for a moment, and just accept the speeds we already have. Take Voyager 1's pace, 17 kilometers a second, our true record for leaving. At that speed, the trip to the nearest star runs about 70,000 years. That is not a number a crew survives. It is a number across which whole species rise and fall. To make 70,000 years real, count generations. A human generation runs about 25 years. 70,000 years is roughly 2,800 generations, one after another, born and grown and gone, the entire span spent inside a single ship between the stars. The people who arrived would be separated from the people who launched by more time than separates us from the first stone tools. No memory, no language, no nation could survive intact across such a gulf. Suppose we managed to go much faster, even 100 times faster than Voyager, which is far beyond anything we can presently build. The trip to Proxima Centauri would still take centuries. A child might be born in transit, live a full life, and die without ever seeing the start or the end of the voyage. Even our wildest near-term hopes do not deliver a journey a single person could live through from departure to arrival. The crossing is generational no matter how generously we count. And Proxima Centauri is the easy case, the closest star of all. Stretch the goal a little to a sun-like star where a more Earth-like world might wait, and the distances jump to tens or hundreds of light years. At our real speeds, those trips run not to thousands of years, but to millions. The galaxy is not a place you visit. At the speeds we can truly reach, it is a place you commit your descendants to, across spans longer than civilization has existed. This is why interstellar travel keeps colliding with biology and time rather than just engineering. A bridge or a tunnel is a problem of materials. A journey of 70,000 years is a problem of mortality. No engine we can presently imagine shortens the trip to within a human life, and no human life stretches to cover the trip. The mismatch is not small. It is a gap of thousands between the decades a person lives and the millennia a crossing takes. There is a tempting reply that we simply need a faster ship, that speed solves everything. And speed does shrink the time, but speed brings its own punishments, ones that grow worse the faster you push, and they begin the moment you try to move quickly through what looks like empty space. For space is not truly empty. There is a thin haze of gas and dust strung between the stars, so sparse that it seems like nothing at all. At a crawl, it is harmless. At a large fraction of the light speed, that same gentle haze turns into a storm a ship must survive. The emptiness between the stars is not as empty as it looks, and that is the next wall. The space between the stars looks perfectly empty, and at human speeds it nearly is. But it is not truly a vacuum. Drifting through it is the interstellar medium, an unimaginably thin haze of gas and dust, mostly hydrogen atoms scattered across the dark. On average, there is only about one atom in every cubic centimetre of interstellar space, a thinness no laboratory on Earth can match. By any everyday standard, it is nothing at all. At a slow drift, that haze does no harm. A spacecraft crossing it at a few kilometres a second sweeps up these stray atoms without noticing. The interstellar medium is so sparse that across the whole width of the solar system, you would gather only a faint trace of gas. This is the emptiness the Voyagers glide through now, untroubled, barely aware the medium is there. Speed changes everything. Push a ship to a large fraction of the speed of light, and those same harmless atoms come at it like a flood. The ship is now slamming into each atom at enormous speed, and a thin gas met at near light speed behaves less like air and more like a stream of radiation. Single hydrogen atoms struck hard enough become a sleet of particles able to bore into metal and damage anything or anyone behind the hull. The haze that was nothing becomes a steady, penetrating storm. The dust is worse than the gas. Scattered among the atoms are tiny grains, specks far smaller than a sand grain. At a crawl, one such grain is a curiosity. At a tenth of the speed of light, a single small grain carries the punch of a bullet, and a larger one the punch of an explosion. A ship racing through the interstellar medium would be sandblasted continuously, its leading face eroded grain by grain, and always at risk of striking one speck large enough to tear straight through. This flips the usual intuition in a hard way. We tend to think the danger of space travel is the emptiness, the vast nothing to be crossed. But for a fast ship, the danger is partly the opposite. It is that space is not empty enough. The faster you go to beat the distance, the more violently the thin medium fights back, until shielding the ship against its own velocity becomes a problem as severe as moving it in the first place, so speed does not come free. Every gain in velocity that shortens the journey also raises the fury of the haze the ship must plough through. A vessel built to cross to another star in a human lifetime would need to survive an unending barrage of gas turned to radiation and dust turned to shrapnel, year after year, with no shelter and no repair. The faster road out is also the more punishing one, and the punishment of the medium is only part of the price of speed. There is a deeper cost written into the physics of motion itself that makes high speed not just dangerous but staggeringly expensive. The energy a ship needs does not climb gently as it goes faster. It climbs steeply, far faster than the speed itself, in a way that turns even modest fractions of light speed into demands beyond anything we can power. To see that, we have to look at how the cost of going fast actually grows. There is a quiet brutality in the physics of going fast, and it lives in a single relationship. The energy of a moving object does not grow in step with its speed. It grows with the square of its speed. Double how fast something moves and you do not double its energy. You quadruple it, triple the speed, and the energy goes up ninefold. The cost of motion climbs far faster than the motion itself. Feel it with something ordinary. A car at 60 kilometers an hour carries a certain energy. The same car at 120, only twice as fast, carries 4 times the energy, which is why a high-speed crash is so much more destructive than a slow one. The damage is not twice as bad. It is 4 times as bad because energy follows the square of speed. This same rule that governs car crashes governs starships. Now scale it up to the speeds a starship needs. To cross to a nearby star within a human lifetime, a ship must reach perhaps a tenth of the speed of light, which is about 30,000 kilometers a second. That is nearly 2,000 times faster than Voyager 1. But because energy grows with the square of speed, the energy needed is not 2,000 times greater. It is that figure squared millions of times greater. The leap from our fastest probe to a true starship is not a long step. It is a chasm in energy. Put a number on it and the demand becomes almost absurd, accelerating even a modest ship weighing no more than a large building. Up to a tenth of light speed would take an amount of energy comparable to everything human civilization produces over many years, poured entirely into one vessel, and that is only to speed it up. To slow down and stop at the far end, you must spend it all again. The arithmetic of speed does not bend for us. It simply states the price, and the price is enormous. This is why faster engines are not a simple fix for the long journey. We cannot just choose to go 100 times faster, because going 100 times faster costs 10,000 times the energy, and we have no power source that can pour out that much into a single moving ship. The slow road takes too long for any crew to survive. The fast road takes more energy than we can generate. Both walls are real, and they press from opposite sides. The square law also explains why every interstellar engine ever sketched reaches for some extraordinary fuel, something far beyond chemical fire. Designers chase nuclear blasts, fusion, even antimatter, not out of ambition but out of necessity, because only the most concentrated energy sources have any hope of meeting the staggering bill that the square of speed presents. We will meet those exotic engines later and see how each one still falls short. But even if energy were free and engines were perfect, one final speed limit would remain, and it is not a matter of cost or fuel. It is woven into the structure of the universe itself. There is a fastest possible speed, a ceiling that nothing with mass can ever reach, let alone cross. That ceiling is the speed of light, and understanding it shows why even the universe's own top speed would not be enough to make the galaxy easily ours. There is a final speed, fixed and absolute, beyond which nothing can go. Light travels at about 300,000 kilometers every second, and that figure is not just the speed of light. It is the speed limit of the universe itself, the fastest that anything, any object, any signal, any influence can ever move. Nothing carrying mass can reach it, and nothing at all can beat it. This ceiling is built into the structure of space and time, discovered by Albert Einstein early in the 20th century. The closer a ship pushes toward that limit, the harder the universe resists. As an object approaches the speed of light, the energy needed to speed it up further grows toward infinity. You can get nearer and nearer to light speed, but you can never arrive, because the last stretch demands more energy than exists. The speed limit is not a wall you crash into. It is a horizon that recedes, always just out of reach, no matter how hard you push. This sets the kindest possible case for any journey. Even at the very edge of physical possibility, travelling just under the speed of light, the trip to Proxima Centauri still takes a bit over 4 years, as measured by people back on Earth, because the star is 4+ light years away and nothing outruns light. To cross the 100,000 light years of the galaxy, even at this ultimate speed, would take 100,000 years by the clocks of home. The universe's own top speed is still far too slow to make the galaxy a quick trip. There is a strange gift hidden here, though, and it is worth being honest about it. Time itself bends at high speed. For a traveller moving very close to the speed of light, time runs slower than it does for the people left behind. A crew racing across the galaxy might feel only a few years pass aboard their ship, even as thousands of years sweep by on Earth. This effect, called time dilation, is real and measured. In principle, a single traveller at near light speed could cross enormous distances within their own lifetime. But notice exactly what time dilation does and does not give. It can let a traveller reach a distant star while staying young. It cannot bring them home to anyone they knew. While a few years pass for the crew, centuries or millennia pass for everyone else. So the travellers arrive in a future utterly cut off from the world they left. And reaching such speed still demands those impossible energies we just met, the ones that climb toward infinity. Time dilation does not lower the price of the ticket. It only changes who ages while it is paid. So even the universe's own speed limit, even with the strange mercy of slowed time, does not hand us the galaxy. The distances are simply too vast for light itself to cross quickly, and we cannot reach light speed in any case. Faced with a journey too long for one life, some have asked a different question entirely. Instead of crossing the gulf within a lifetime, why not build a ship that carries many lifetimes inside it? A small moving world where generations are born, live, and die on the way. That idea has a long history and its own deep problems. If no engine can shorten the journey to within a single life, then perhaps the answer is to stop fighting time and build a ship made to outlast its crew. This is the idea of the generation ship, a vessel so large and self-sustaining that the people who arrive are the distant descendants of the people who left. No one aboard would see both the launch and the landing. They would live their whole lives in transit on a world that happens to be moving between the stars. Such a ship could not be a cramped capsule. It would have to be a closed living world, large enough to grow its own food, recycle its own air and water, and hold a whole community across many centuries. Picture a vast spinning cylinder, its inner surface lined with fields and homes, the spin pressing people gently against the walls to mimic gravity. Everything a human society needs would have to be packed inside and kept working, without resupply, for longer than any nation on Earth has lasted. The hardest problems are not in the engines but in the people. A closed colony must sustain enough genetic diversity to stay healthy across many generations. Studies of this question suggest a viable crew would need to number at least several thousand, perhaps far more, to avoid the slow damage of breeding within too small a group. A handful of pioneers would not do. To cross the stars, you must launch something closer to a small town and keep it whole for centuries. We have a sobering real-world lesson in how hard a closed world is to run. In the early 1990s, a sealed habitat called Biosphere 2 was built in the Arizona desert, and 8 people locked themselves inside to live off its enclosed ecosystem. Within months, the oxygen mysteriously fell, crops struggled, and the careful balance kept slipping out of true. That experiment lasted only 2 years, on Earth, with rescue a phone call away. A generation ship would have to do the same thing flawlessly for centuries, with no outside air and no way home. Then there is the human side, harder to engineer than the air. A generation ship asks people to be born into a journey they did not choose, to spend their entire lives serving a destination they will never see, and to raise children bound by the same fate. The society aboard would have to hold together across centuries of confinement, without collapse, without forgetting its purpose, without the knowledge and skills decaying over the long dark. No human community has ever stayed stable and intact for that long, even on a whole planet. So the generation ship trades one impossible problem for another. It sidesteps the need for blinding speed, but only by demanding a sealed world that runs perfectly for centuries, and a society that endures with it. We can sketch such a ship. We cannot yet build a closed ecosystem that lasts even a few years, nor do we know if any human culture could survive the crossing whole. The journey might still arrive. We simply cannot say a recognizable humanity would arrive with it. There is another way to cross a journey longer than a life, one that does not ask generations to live and die along the way. Instead of filling the centuries with new lives, it tries to pause life itself, to let a single crew sleep through the long dark and wake at the far end. That dream of the long sleep is old and powerful, and it runs into the stubborn facts of the living body. If a crew cannot survive a journey of centuries by living through it, perhaps they could survive by not living through it, by sleeping the whole way. This is the dream of suspended animation, of slowing the body so deeply that it barely ages, so a traveller might lie down at launch and wake, almost unchanged on arrival. It would let a single crew cross a gulf no waking life could span. The idea is everywhere in stories. The reality is far more stubborn. Nature does offer a hint that life can be paused. Many animals enter deep states of slowed living to survive harsh seasons. A hibernating ground squirrel drops its body temperature near freezing, slows its heart to a few beats a minute, and passes the winter in a kind of suspended state, then revives in spring. Some frogs freeze nearly solid and thaw back to life. These creatures show that a body can, in some forms, be slowed almost to a stop and brought back. The question is whether a human body could ever do the same, for years, without harm. So far, the honest answer is that it cannot, not yet, and perhaps not for a very long time. Medicine has learned to cool patients for a few hours during certain surgeries, lowering the body's temperature to buy time. Space agencies have studied a milder sleep-like state called torpor as a way to ease the months-long trip to Mars. But these reach for hours or days, not the years or centuries a starship would demand. Stretching a human pause from hours to centuries is not a small step. It is a leap into the unknown. The body fights against being paused. Cells keep working at some level even when chilled, and over long spans that slow activity does steady damage. Freezing a person solid, as is sometimes imagined, creates a worse problem, because water expands as it turns to ice, and the ice crystals tear delicate cells apart from within. The very act of freezing destroys the tissue you hope to preserve. Living matter is not a machine you can simply switch off and on. It decays the moment it stops maintaining itself. There is also the matter of waking. Even if a body could be held for centuries, every system would have to restart in perfect order. The heart, the brain, every organ resuming together after ages of stillness. We have no method that can do this, and no certainty that it is even possible for a complex human being. A sleep that cannot be safely ended is not suspended animation. It is simply an end. So the long sleep, like the generation ship, remains a hope rather than a tool. It would solve the problem of time beautifully, letting one crew skip across the centuries. But the living body, with its restless cells and its fragile chemistry, does not yet allow it, and may never. We cannot reliably pause a person for a single year, let alone the thousands a journey might take. Every path we have walked so far, the fast ship, the slow ship, the sleeping crew, runs into a wall. Yet all of them have assumed the goal is to reach another star within the galaxy. The deeper question tonight is bigger. It is whether we could ever leave the galaxy itself, break free of the whole Milky Way, and that turns out to be governed by a grip far stronger than any we have met, the gravity of the galaxy as a whole, holding everything within it at a speed we can scarcely imagine reaching. Every gravitational hold we have met has its own escape velocity, its own speed you must carry to break loose. The Earth's is 11 kilometers a second. The Sun's, from where we orbit, is about 42. Now ask the largest version of the question. How fast must something move to escape not the Earth, not the Sun, but the entire Milky Way galaxy, to climb out of its gravity altogether and never fall back? The answer is the steepest wall of all. From our place out in the disk, the galactic escape velocity is somewhere around 550 kilometers every second. That is the speed an object here must reach to leave the galaxy for good. Set it beside the others, and the scale becomes clear. To escape the Earth, 11 kilometers a second. To escape the Sun, about 42. To escape the whole galaxy, roughly 550, more than 13 times the Sun's wall and 50 times the Earth's. The Milky Way holds us in a well far deeper than the Sun's, and the Sun's already defeated our best rockets. Compare that figure to what we can actually do. Voyager 1, our fastest outbound craft, moves at 17 kilometers a second. Galactic escape demands more than 500. We're not slightly too slow. We're slower by a factor of more than 30, and that gap, recall, is in speed, while the energy needed grows with the square of speed. In energy terms, leaving the galaxy is roughly 1,000 times harder than the already impossible task of pushing a ship to galactic escape speed by ordinary means. This is the heart of the matter, the real reason the title frames an honest doubt. The galaxy is not just far across, it is a deep gravitational well, and we sit well down inside it, out on the rim where the well is still profound. To leave, a ship would not merely have to cross great distances, it would have to reach a speed of hundreds of kilometers a second and hold it, climbing for tens of thousands of light years against a pull that never fully releases, exactly as a thrown ball climbs against the Earth, but on a scale beyond all our machines. And the figure of 550 kilometers a second comes with a twist that makes the well deeper than the stars alone can explain. When astronomers add up all the visible matter in the galaxy, every star, every cloud of gas, every speck of dust, they find it is nowhere near enough to require an escape speed that high. The galaxy pulls far harder than its glowing contents should allow. Something unseen is adding most of the grip, holding the galaxy together and holding us within it. That something is the largest part of the galaxy by far, and it is invisible. It does not shine, does not block light, does not announce itself in any telescope. We know it only by its pull, by the way the galaxy turns and the way it holds. It is called dark matter, and it means the wall around us is built mostly from a substance we have never seen and do not understand. To finish mapping the grip that holds us, we have to face this unseen mass directly. The galaxy weighs far more than its stars. When astronomers tally everything that shines, every star, every glowing cloud, every visible speck, and ask whether that mass is enough to explain how the galaxy behaves, the answer comes back wrong by a wide margin. The Milky Way pulls far harder than its visible contents can account for. Most of what holds the galaxy together gives off no light at all, and we call it dark matter. The first clear sign came from watching how galaxies spin. In the 1970s, the American astronomer Vera Rubin, working with Kent Ford, carefully measured how fast stars orbit at different distances from a galaxy's centre. By the ordinary rules of gravity, stars far out on the edge, where the visible mass thins to almost nothing, should orbit slowly, the way distant planets circle the sun more slowly than near ones. Instead, Rubin found the outer stars racing along just as fast as the inner ones, as though held by far more mass than any telescope could see. There was only one way to read it. A vast amount of unseen matter must be spread through and around each galaxy, its gravity gripping the outer stars and whipping them along. The visible disk of bright stars turned out to be only the inner glowing part of something much larger and heavier, a great hidden halo of mass reaching far beyond the light. An earlier astronomer, Fritz Zwicky, had hinted at this as far back as the 1930s, studying how clusters of galaxies moved, and had given the unseen stuff a name that stuck. The numbers are humbling. By the best accounting, the ordinary visible matter, the stars and gas and dust, makes up only a small fraction of the galaxy's true mass. The great majority, something like 5 or 6 times as much, is this dark matter, present everywhere yet seen nowhere. We do not know what it is. It does not appear to be made of ordinary atoms. It passes through everything, including us and the Earth, untouched, betraying itself only through its gravity. This is what deepens the well that holds us. The galactic escape velocity of 550 kilometers a second is so high, precisely because the galaxy is so much heavier than it looks. Most of the grip on us comes not from the stars we can see, but from this invisible halo, a sphere of unknown substance many times more massive than all the suns combined, wrapped around the whole Milky Way. We're held down not mainly by the bright band overhead, but by a vast dark thing we cannot point to. There is something almost vertiginous in this. The wall we would have to climb to leave the galaxy is built largely from a material no one has ever directly detected. We can measure its pull with precision, calculate the speed needed to overcome it, and yet we cannot say what it is. The deepest part of our prison is made of the most mysterious stuff in the universe, so the grip is fully mapped and it is formidable. A deep gravitational well, demanding hundreds of kilometers a second to escape, most of it sourced from unseen mass. We have walked the layered holds from the Earth at our feet to the dark halo at the galaxy's edge. The next question is one of strategy. If the well is this deep, which way should a ship even point to climb out of it most easily, across the long disk or straight up through its thin face? The answer reshapes the whole problem. If the galaxy is a deep well, the next question is purely practical. Which way should a ship climb to get out with the least effort? The instinct is to think of crossing the galaxy, of travelling the 100,000 light years from one rim to the other. But that is the hardest possible path, the long way through the thickest part of everything. The smart way out is not across the wheel at all, It is straight up, out through the flat face of the disk. Remember the shape. The Milky Way is a broad, thin plate, 100,000 light-years wide but only about 1,000 light-years thick. We live inside that thin layer, roughly in its middle. In the plane of the disk, stars and gas stretch away for tens of thousands of light-years in every direction. But above and below us, perpendicular to the plate, the galaxy is shallow. Go up, and you are out of the bright disk in only a few hundred light-years. So a ship trying to leave should point away from the disk, toward the empty sky above or below the band of the Milky Way, not along it. In that direction the road is shortest, the stars thin out fastest, and the dust and gas of the disk fall away soonest. You would rise out of the crowded plane and into the quiet of the halo, where the night holds almost no nearby stars, only the distant glow of the disk receding beneath you, like a city seen from a climbing plane. This does shorten the distance, and meaningfully. Instead of 50,000 light-years to the visible edge across the disk, the climb out the top is closer to a few hundred light-years to clear the bright layer, and 1,000 or two to rise well clear of it. By the measure of distance alone, leaving the disk is far easier than crossing it. If distance were the only wall, going up would make escape merely very hard rather than unthinkable. But distance is not the only wall, and this is the quiet sting of the chapter. The gravitational well does not care which way you climb. Whether you head out across the disk or straight up through its face, you still have to overcome that same galactic escape velocity, that same 550 kilometers a second set by the total mass of the galaxy and its vast dark halo. The halo of dark matter reaches far above and below the disk, so climbing out the thin way does not let you dodge the grip. You leave the stars behind quickly, but the pull follows you up. So the shortest way out solves the smaller problem and leaves the larger one untouched. Going up spares you most of the distance, but none of the speed. You would still need to be moving at hundreds of kilometers a second to keep rising forever and never fall back into the galaxy's embrace. The thin face of the disk is a shortcut through the light, not through the gravity. It helps to know that real objects do this, that galactic escape is not only a number on paper. Out there, rarely, a star is flung upward and outward fast enough to leave the Milky Way entirely, climbing out of the well and never returning. These are the stars that got away, moving at speeds that dwarf anything in our quiet neighborhood. They show us exactly what true galactic escape looks like, and exactly how violent the launch must be to achieve it. Most stars in the galaxy move together in a calm, orderly march, circling the center at a couple of 100 kilometers a second, all flowing the same way like a vast school of fish. But a rare few break ranks entirely. They tear through the galaxy at extraordinary speeds, hundreds of kilometers a second faster than everything around them, moving so quickly that the Milky Way cannot hold them. Astronomers call them hypervelocity stars, and they are the only things we know of that actually escape the galaxy. The first ones were found in the early 2000s, stars clocked moving so fast against the general flow that their paths could only end one way, by leaving the galaxy altogether. They are climbing the same well we have been describing, except they are climbing it fast enough to win. A hypervelocity star is on a one-way trip out of the Milky Way, destined to spend the rest of its long life drifting in the empty space between galaxies, falling away from the wheel of light that made it. The most striking example yet found is a star catalogued as S5HVS1. Discovered in 2019, it was clocked moving at roughly 1,700 kilometers every second. Sit with that figure. It is about 100 times faster than Voyager 1, and more than 3 times the speed needed to escape the galaxy. It is, by a wide margin, one of the fastest stars ever measured, a whole sun hurled outward at a velocity no machine of ours could approach. That speed is the honest benchmark for galactic escape. To leave the Milky Way, you do not need to be a little faster than the stars around you. You need to be moving at many hundreds of kilometers a second in the range these rare runaways reach. S5HVS1 shows the scale plainly. The galaxy can be left, but only at speeds that make our fastest probe look frozen in place, speeds reached by flinging an entire star like a stone from a sling. And that is exactly what happened to it. By tracing the path of S5HVS1 backward, astronomers found that it came from the very centre of the galaxy, from the crowded core where stars swarm thickly around something enormous. It was not born moving this fast. It was thrown, accelerated to its tremendous speed in a single violent encounter at the galactic centre, then sent racing outward along a path that will carry it clean out of the Milky Way and into the dark beyond. So the stars that escape do not build up their speed gradually, the way a rocket would. They are launched in one brutal event by the most powerful engine the galaxy contains. No gentle, patient acceleration lifts a star out of the well. It takes a sudden, colossal kick, delivered by a force far beyond anything we could build or harness, operating at the dense and dangerous heart of the galaxy. This points us straight at that heart, because the engine that flings these stars free is one specific object, and it is the most extreme thing in the entire Milky Way. At the very centre, where S5HVS1 was thrown, sits a mass so concentrated that not even light can climb out of it. It is the galaxy's central black hole, and understanding how it launches stars to escape velocity shows both the only natural way out of the galaxy and why that way is forever closed to us. At the very centre of the Milky Way, 26,000 light-years from where we sit, lies an object of almost unimaginable density. It is a black hole, a place where so much mass is packed into so small a space that its gravity allows nothing to escape, not even light. We call it Sagittarius A star, after the constellation we see it through, and it holds the mass of about 4 million suns compressed into a region that would fit inside the orbit of the planets. For a long time it was only suspected. Then astronomers watched the stars nearest the centre, tracking their motion year after year, and saw them whipping around a single invisible point at tremendous speed, some completing tight orbits in just a few years. Only an enormous unseen mass could swing whole stars around so fast. The team that mapped these orbits, led by Reinhard Genzel and Andrea Ghez, working separately over decades, earned a share of the Nobel Prize in 2020 for proving the dark heart of our galaxy is real. This is the engine that makes hypervelocity stars. When a pair of stars, two suns orbiting each other, wanders too close to Sagittarius A star, the black hole's immense gravity can seize one and capture it, while flinging the other away with a violent slingshot kick. The captured star is pulled into the maw, its partner is hurled outward at 1,000 or more kilometers a second, fast enough to cross the whole galaxy and escape. S5HVS1 was very likely launched in exactly this way, torn from a companion and thrown clear. So the galaxy does have a way to fling things out into the void. It is the central black hole, a gravitational catapult of staggering power. But notice what that way requires. To be ejected, a star must fall almost to the very centre of the galaxy, into the crowded, radiation-soaked region around the black hole, and survive a close pass with an object that swallows light. The price of the catapult is a brush with destruction. The only natural exit from the Milky Way runs through its most lethal point. This shows, with brutal clarity, what it costs to truly leave. The galaxy does not let anything out gently. The one mechanism that reliably hurls matter past escape velocity is a near collision with a 4 million solar mass black hole, an encounter no ship and no crew could survive, and one we could never aim or control. The exit exists, but it is not a door we can use. It is a catastrophe that happens to occasional stars. There is a quiet irony in it. The same gravity that holds us down in the well is, at the galaxy's centre, concentrated enough to throw stars clean out of that well. The deepest part of the trap is also the only launch pad. But the launch is indistinguishable from disaster, available only to objects that fall into the worst place in the galaxy and happen to be slung out rather than swallowed. If nature's only escape route is closed to us, then any real hope of leaving has to come from engines of our own making. And so the search turns inward, to human designs, to the engineers and physicists who have asked how we might generate by ourselves even a fraction of the speed these runaway stars are given for free. The first serious answer was bold and almost unbelievable: a ship that would move by riding the force of nuclear explosions, one blast at a time. If chemical fuel is far too weak to reach the stars, the obvious thought is to reach for the most violent energy we know. In the late 1950s, a team of American scientists did exactly that and designed a starship that would ride nuclear explosions. The project was called Orion, and the idea was as audacious as it sounds. You would build a massive ship with a thick plate on its underside, and behind that plate you would detonate atomic bombs, one after another, letting each blast slam the ship forward. The design was strange but serious. A long series of small nuclear bombs would be dropped behind the ship and exploded a short distance away. Each explosion would hammer against a heavy pusher plate, shoving the vessel ahead, while giant shock absorbers smoothed the brutal kicks into a steady push. The ship would not sip fuel. It would buck forward on a string of atomic blasts, a new bomb every few seconds, climbing towards speeds no rocket could touch. And the numbers were genuinely promising, which is what makes Orion more than a curiosity. Nuclear explosions carry millions of times more energy per kilogram than chemical fuel, so a ship riding them could in principle reach a few % of the speed of light. That is enough to make the nearest stars thinkable within a long human lifetime or two, rather than tens of thousands of years. Of all the early starship ideas, Orion was the one built on real, proven physics, on bombs we already knew how to make. The people who worked on it, including the physicist Freeman Dyson, took it seriously enough to study it in detail. They imagined ships carrying not a tiny capsule, but a substantial crew and cargo, whole pioneering parties, pushed outward by the same nuclear force that the world had just learned to fear. For a brief moment in the early 1960s, riding atomic bombs to the stars looked like something we might actually attempt. But Orion ran into walls both practical and human. To launch from Earth, it would set off nuclear blasts in the atmosphere, scattering radioactive fallout across the sky with every detonation. In 1963, the Partial Test Ban Treaty outlawed nuclear explosions in the atmosphere and in space, and that sensibly ended any thought of bomb-driven launches from the ground. The very thing that made Orion powerful, the nuclear blast, made it unusable in the world we actually live in. And even Orion, for all its power, falls far short of the real question tonight. A few % of light speed is a triumph against the distance to the nearest stars, but it is nowhere near the hundreds of kilometers a second needed to climb out of the galaxy, and it is reached by a method we cannot responsibly use. Orion could perhaps carry people to a neighbouring sun, given enormous will and cost. It could not lift them out of the Milky Way, and it could not fly without spreading the very poison it ran on. Still, Orion taught a vital lesson. To cross interstellar distances, you must abandon chemical fire entirely and tap into the nuclear forces that bind the atom. Orion did this with crude, explosive bombs. The natural next thought is to harness that same nuclear energy in a cleaner, more controlled way, not by detonating bombs, but by running a steady nuclear furnace, the same process that powers the sun. That hope took shape in a careful, detailed starship design built around fusion. If exploding bombs behind a ship is too crude and too dirty, perhaps we can tame nuclear energy instead of detonating it. The sun runs on fusion, the merging of light atomic nuclei into heavier ones, releasing torrents of energy in the process. A fusion rocket would carry that same reaction aboard, fusing atoms in a controlled stream and firing the hot product out the back at tremendous speed. It would be a small, steady star harnessed for thrust, far cleaner and more efficient than any string of bombs. In the 1970s, a group of engineers with the British Interplanetary Society sat down to design such a ship in real detail, not as a fantasy but as a serious engineering study. The project was called Daedalus, and its goal was a flyby of Barnard's star, a dim red star about 6 light-years away, within a single working lifetime of roughly 50 years. They wanted to prove that a starship could be sketched with the physics we actually understand, using only modest extensions of known science. Daedalus was enormous. It would be a 2-stage vehicle taller than a skyscraper, most of it fuel, designed to burn tiny pellets of fusion fuel, igniting them many times a second with beams of electrons. The fuel itself was exotic, including a rare form of helium that is scarce on Earth and would have to be mined from the atmosphere of Jupiter. The plan called for the ship to be built in space and to accelerate for years, slowly building up to about 12% of the speed of light. At that speed, the trip to Barnard's star would take around 50 years, and the ship would scream past its target in a matter of hours, gathering what data it could as it flew through the distance system without stopping. There was no plan to slow down, because slowing down would have doubled the already staggering fuel requirement. Daedalus was a one-way arrow, meant to prove that a probe could reach another star, not to deliver anyone there to stay. The study was careful and sober, and its conclusion was encouraging in one way and humbling in another. It showed that a fusion starship is not forbidden by physics, that we can at least design one on paper using fuels and forces we understand. But it also showed the staggering scale required, a ship of tens of thousands of tons, most of it rare fuel built in orbit, to send a single uncrewed probe past one nearby star at 1/10 of light speed. And Daedalus, like Orion, does nothing to answer the larger question. 12% of the speed of light is a marvel for crossing to a neighbour sun, but it's still far below galactic escape velocity, and it carries no crew, only instruments. A fusion rocket might one day fling a robotic probe to Barnard's star or Proxima Centauri. It would not carry a living person out of the galaxy, or even, in its sketched form, carry a person to another star and stop. Fusion takes us further than bombs, but it still leaves us inside the well, moving at a small fraction of light speed. To go faster, designers reached for the most concentrated energy source the universe allows, a substance that turns its entire mass into pure energy when it meets ordinary matter. It promises far more than fusion, enough in principle to approach light speed itself. It is antimatter, and its promise and its impossibility are matched in equal measure. There is a fuel so potent that nothing in nature beats it, a substance that releases every scrap of its mass as energy. It is called antimatter, and it is real, not science fiction. For every kind of ordinary particle, physics allows a mirror image partner with opposite charge. An ordinary electron has an antimatter twin called a positron. When a particle of matter meets its antimatter twin, both vanish instantly, and their entire mass converts into a burst of pure energy. Nothing is left behind but radiation. This is what makes antimatter the ultimate fuel. When you burn chemical fuel, you convert a tiny fraction of its mass into energy. Even nuclear fusion, the power of the sun, releases less than 1% of its fuel's mass. But matter meeting antimatter converts the full 100%, the entire mass on both sides, into energy. Gram for gram, antimatter carries roughly 1,000 times the energy of fusion, and billions of times the energy of chemical fire. A handful could in principle drive a ship toward a real fraction of light speed. The physics is sound, and antimatter genuinely exists. We make it, in vanishing amounts, in great particle accelerators like the ones at CERN, where atoms are smashed together at high energy. We have even made and briefly held complete atoms of antihydrogen, the antimatter version of the simplest atom. So this is not a fantasy substance. It is something we have created, measured, and studied in the laboratory, a fuel whose power is beyond question. The problem is making enough of it, and the gap there is almost beyond words. All the antimatter humanity has ever produced, gathered across decades of work at every accelerator on Earth, would amount to far less than 1/1,000,000 of a gram. To drive a starship, you would need not micrograms but tons of it. At our present rate of production, manufacturing a single gram of antimatter would take vastly longer than the age of the universe, and cost more than the wealth of nations. We can make it, but only in specks, at staggering expense. And even if we somehow made enough, we could not store it. Antimatter destroys itself the instant it touches ordinary matter, so it cannot be kept in any normal container, because the walls themselves would annihilate it. It would have to be held suspended in a perfect magnetic trap, never touching anything, kept apart from all ordinary matter for the entire voyage. A single failure, a moment's contact, would release the full energy of all that fuel at once, in a blast beyond any bomb. Carrying tons of antimatter would mean carrying the most dangerous cargo imaginable. So antimatter sits at a cruel crossroads. It is the one fuel powerful enough to push a ship toward the speeds that might make starflight swift, and it is, by an enormous margin, the hardest thing in the universe to make and to hold. The energy is there. The means to gather and contain it are not, and may never be. The perfect fuel is also the impossible one. With antimatter, the search for a better engine reaches the edge of what raw energy can offer, and still falls short of easy starflight. So designers tried a completely different approach, one that carries no fuel at all. Instead of pushing a ship from within, why not push it from the outside with light itself, and leave the heavy engine behind on the ground? Every engine so far has carried its own fuel, and the rocket equation punishes that mercilessly, because the ship must haul the very propellant that moves it. But there is a way to escape the trap entirely. Leave the fuel behind. Light itself carries a tiny push, a faint pressure that sunlight exerts on anything it strikes, and a large, thin sail could catch that push and ride it, needing no engine and no tank at all. The push is real but gentle. Sunlight falling on a surface presses on it ever so slightly, a force far too weak to feel but steady and endless. A spacecraft fitted with a vast mirror-thin sail, kilometers wide yet lighter than a sheet, could catch the sun's light and be pushed gradually outward, gaining speed day after day for free. There is no fuel to run out, only the endless pressure of light. Japan's Ikaros mission, launched in 2010, unfurled such a sail in space and proved that sunlight alone can drive a craft, the first to truly sail on light. Sunlight fades with distance though, so to reach real speed the idea is sharpened. Instead of relying on the distant sun, you build a powerful laser back home and aim its concentrated beam at the sail, pushing far harder than sunlight ever could. A giant laser on Earth or in orbit could drive a sail to enormous speed while the heavy machinery stays safely behind, never leaving the ground. The ship becomes almost nothing but sail and payload, and all the power comes from a beam that chases it outward. This is the heart of a real project called Breakthrough Starshot, announced in 2016 with backing from serious scientists and large funding. Its plan is strikingly clever. Instead of a heavy crude ship, send something tiny, a microchip the size of a postage stamp carrying cameras and sensors and trailing a small light sail just meters across. A powerful array of ground-based lasers would fire at the sail for a few minutes, pushing the featherweight craft to about 20% of the speed of light. At that speed, the little probe could reach Proxima Centauri in roughly 20 years, then beam its findings back across the 4 light-years to Earth. A fleet of these chips, launched in waves, could give us our first close look at another star system within a single human lifetime. It is, by far, the most realistic plan anyone has for actually reaching another star in the near future, and it sidesteps the rocket equation completely by carrying no fuel of its own. If you take one idea from tonight about how starflight might really begin, let it be this one, and consider following along as the science unfolds. But notice what Starshot achieves and what it does not. It can fling a gram-scale chip to a fifth of light speed. It cannot push a human being or anything heavy, because the same laser that hurls a postage stamp would barely nudge a crude ship that weighs millions of times more. and 20% of light speed, marvellous as it is for a tiny probe, is still far below galactic escape and carries no one outward at all. So even the cleverest fuel-free design reaches only a sliver of what leaving the galaxy would demand, and only for the smallest possible payload. With ordinary engines exhausted, some have looked past pushing a ship through space at all, and ask whether space itself might be moved instead. Every method so far obeys the same hard rule that nothing with mass can reach the speed of light, and so the stars stay agonizingly far. But in 1994, a Mexican physicist named Miguel Alcubierre asked a different question. What if you did not move the ship through space at all, but moved space itself around the ship? The idea sounds like fantasy, yet it came straight out of Einstein's own equations, the mathematics that describes how space and time bend. Einstein showed that space is not a fixed stage but a flexible fabric that can stretch, compress and curve. Alcubierre's idea took that seriously. Imagine a ship sitting inside a small bubble of flat, ordinary space. Behind the bubble you stretch and expand space, pushing the bubble forward. In front of it, you compress and shrink space, pulling the bubble ahead. The ship inside never moves through space at all. The bubble of space carries it, like a surfer resting motionless on a wave that sweeps them along. The beauty of the idea is that it dodges the light speed limit on a technicality. That limit applies to objects moving through space, but space itself has no such cap. The expansion of the universe already carries distant galaxies apart faster than light, not because they move, but because the space between them grows. A warp bubble would use the same loophole. The ship would sit still inside its bubble while space did the travelling, and could in principle cross to a distant star in a short time, without ever locally breaking the speed of light. For a moment this seems like the escape from every wall we have met. No fuel hauled, no rocket equation, no crushing energy of acceleration, no centuries of travel. A warp drive, if it worked, would make the galaxy genuinely crossable, even leaving it conceivable. This is why the idea captured so many imaginations, because it is not a violation of physics, but a strange and clever reading of the very equations we trust. But the catch is severe, and honesty requires facing it. To bend space in the way Alcubierre described, you would need a kind of matter that, as far as we know, does not exist. Stretching space behind the ship and compressing it ahead requires negative energy, a substance with negative mass, something that pushes where ordinary matter pulls. We have never found such material in any usable form. Hints of negative energy appear in delicate laboratory effects, but nothing remotely like the vast amount a warp bubble would demand, and the amount needed is staggering. Early estimates suggested a warp drive would require more negative energy than exists in the entire visible universe, an absurd and disqualifying figure. Later work has trimmed that number, imagining cleverer bubble shapes that need far less, yet still far more than anything we can conceive of making, and still made of a substance no one has ever held. The warp drive remains a line of beautiful mathematics, fully consistent on paper, with no known way to build it. So the most hopeful idea of all sits in a strange place, neither proven impossible nor remotely achievable, a door that the equations seem to allow but that we have no key to open. It may be a genuine loophole awaiting a discovery we have not made, or it may be a mirage that dissolves on closer study. Either way, it is not a ship we can build, and with the warp drive set aside, we can finally line up every engine we have imagined and measure them all against the one number that matters. We have now walked through every serious idea humanity has for crossing the void, from the crude power of bombs to the strange mathematics of warped space. It is worth lining them all up against the single number this whole journey turns on, the galactic escape velocity of roughly 550 kilometers a second, the speed needed to climb out of the Milky Way for good. Held against that figure, the verdict is stark. Start with what flies today. Voyager 1 moves at 17 kilometers a second, about 3% of what galactic escape requires. Our fastest real machine is not within sight of the number. It is slower than the goal by a factor of more than 30, and that is the best our actual hardware can do after decades of effort. Nothing we have ever launched comes close. Now bring in the designs that exist only on paper, but built from real physics. Project Orion, riding nuclear bombs, might have reached a few percent of light speed, which is several thousand kilometers a second, finally clearing galactic escape velocity with room to spare. Project Daedalus, on fusion, aimed for 12% of light speed, well above the escape number 2. Breakthrough Starshot on a laser-push sail targets 20% of light speed. So on raw speed alone, 3 of our boldest concepts could, in principle, exceed the speed needed to leave the galaxy. But raw speed is not the whole test, and here the designs fall apart. Orion could not launch without scattering nuclear fallout and breaking treaties, and even at its best it carries a heavy crew only to a nearby star, not out of the galaxy. Daedalus, at galaxy escaping speed, is a one-way uncrewed probe the size of a skyscraper that cannot slow down. Starshot reaches its speed only by shrinking the payload to a gram, a chip that could never carry a person. The moment you ask any of them to carry a living human out of the Milky Way, the numbers collapse. The reason is the cruel partnership of speed and energy. To carry a person, you need mass, a ship with air and water and shelter, and the means to keep someone alive for the journey. But the energy to push mass to galaxy escaping speed grows with the square of that speed and in direct proportion to the mass. So a crewed ship at 500 kilometers a second demands energy beyond anything we can generate, by a margin of thousands or more. The light designs reach the speed only by abandoning the crew. The crewed designs keep the crew only by abandoning the speed. So every engine stops short, each in its own way. Some are fast but empty. Some could carry people but only slowly, to a single nearby star at best, never out of the galaxy. And the one idea that might carry people swiftly across any distance, the warp drive, needs a substance we have never found and may never find. There is no design on the table, real or sketched, that takes a human being out of the Milky Way. Not one. This is the honest engineering answer to the title's question. It is not that we lack imagination, for we have imagined boldly. It is that the gap between any payload we could keep alive and the speed it would need is too wide for every tool we have or can foresee. And yet, even granting all this, there is a still larger reason the galaxy holds us, one that has nothing to do with engines and everything to do with the company the Milky Way keeps in the dark around it. Step back far enough from the Milky Way and a new picture appears, one that makes the question of leaving even harder. Our galaxy is not alone in empty space. It belongs to a small cluster of galaxies bound together by gravity called the local group. The Milky Way is one of its 2 giants. The other is the Great Spiral of Andromeda, our nearest large neighbour, lying about 2.5 million light-years away. The local group holds more than 50 galaxies in all, but most are small. There is the Milky Way and Andromeda, the 2 heavyweights, and a third, smaller spiral called the Triangulum Galaxy. Around and between them drift dozens of dwarf galaxies, faint scatterings of stars held in the same gravitational embrace. Together, this whole collection spans about 10 million light-years and moves through the universe as a single bound family, its members tied to one another by mutual gravity. Being bound is the key word. Just as the sun's gravity holds the planets, and the galaxy's gravity holds the stars, the combined gravity of the local group holds its galaxies together. They are not flying apart. They orbit and weave around a shared centre of mass, locked in a slow gravitational dance that will continue for ages. The local group is itself a kind of well, a larger basin of gravity within which the Milky Way sits as one part. This adds a further layer to everything we have said about escape. Even if, against all the engineering walls, a ship somehow climbed out of the Milky Way's own gravity, it would still find itself inside the larger grip of the local group, still bound to the family of galaxies, still unable to drift freely away. The dark matter that deepens the Milky Way's well extends in even greater amount around the whole local group, binding the giant galaxies to one another. Leaving the Milky Way would not mean leaving the neighbourhood, and the neighbourhood is not static. Andromeda and the Milky Way are not simply sitting at a fixed distance. They are falling toward each other, drawn together by their mutual gravity, closing the gap between them at about 110 kilometres every second. The two greatest galaxies of the local group are on a slow collision course, bound so tightly that they are destined not just to stay together but to merge into one. So the Milky Way is held within a structure larger than itself, and that structure is in motion, its two great spirals drifting toward a meeting. The gravity that ties us down does not end at the edge of our own galaxy. It reaches out to embrace Andromeda and dozens of smaller galaxies, a wider web of pull that any true escape would also have to overcome. We are bound not just to a galaxy, but to a small confederation of galaxies, all falling slowly together. That coming together is one of the great events written into the future of our sky. Long after the questions of starflight are settled one way or another, the two galaxies will reach each other and become something new. Looking ahead to that collision shows both how dynamic our seemingly fixed galaxy really is, and what kind of sky our distant descendants, if any remain, would inherit. The night sky looks permanent, the same stars our ancestors saw, the same band of light. But it is changing slowly, on a scale of time so vast that no human eye could ever catch it in motion. The Andromeda Galaxy, that faint smudge of light visible on a dark autumn night, is drifting toward us, and in the deep future it and the Milky Way will collide and merge. The two grandest spirals of our local group are destined to become a single galaxy. The collision will begin in roughly 4 billion years. When it does, it will not be the violent smash the word collision suggests. Galaxies are mostly empty space, with vast gulfs between their stars, so when two galaxies pass through each other, almost no stars actually strike. Instead, the two great pinwheels will glide into one another, their gravity tugging their spiral arms into long streaming tails, pulling and stretching each other over hundreds of millions of years in a slow, silent dance. Over time, the two galaxies will swing apart, fall back, and pass through each other again, their structures unravelling a little more with each pass. Eventually they will settle together for good, their stars mingled, their spiral shapes gone, blended into a single vast elliptical galaxy, a great smooth ball of stars with no arms at all. Astronomers have even given the future merged galaxy a name, Milkdromeda, a blend of the two that made it. The familiar wheel we live in will, in the end, cease to exist as we know it. For any world that survives to see it, the sky would be transformed. As Andromeda drew closer over the eons, it would swell from a faint smudge into a great glowing spiral filling a huge swath of the night, brighter and larger with each passing million years, until two galaxies blazed overhead at once. It would be one of the most spectacular sights the universe can offer, unfolding far too slowly for any single creature to witness, written across spans of time that dwarf all of life's history. What of the Sun, and any descendants of Earth during all this? The Sun will likely survive the merger itself, since direct collisions between stars are so rare, but the gravitational chaos could fling our solar system into a wildly different orbit, hurling it far out into the new galaxy's halo, or in rarer cases even casting it out altogether. By then, though, the Sun will be nearing the end of its own life, swelling toward the red giant phase that will scorch the Earth. So the merger is a distant backdrop to a closer ending. This long story carries a quiet message for the question of leaving. The galaxy that holds us is not a fixed prison with stable walls. It is a living, moving thing, destined to merge with another and become something new. Even on the grandest scale, change is happening, just unbearably slowly. The Milky Way our descendants might inherit would not even be the Milky Way, but Milkdromeda, a galaxy reshaped by a collision 4 billion years in the making. Yet even as Andromeda falls toward us, the wider universe is doing the opposite. Beyond our bound local group, the galaxies are not drawing closer. They are racing away, and faster every year, carried apart by a force discovered only recently that is reshaping the very meaning of distance. That force makes the question of leaving not just hard, but for everything beyond our small group, permanently and increasingly hopeless. Within our local group, gravity rules, holding the Milky Way and Andromeda together. But look beyond that small-bound family, out to the other galaxies scattered across the universe, and something stranger is happening. They are all moving away from us. Nearly every distant galaxy is receding, and the farther away one is, the faster it flees. The whole universe is expanding, the space between the galaxies stretching and growing in every direction at once. This was discovered in 1929 by the American astronomer Edwin Hubble, who found that the light of distant galaxies was stretched toward redder colours, the signature of objects rushing away. He saw a clear pattern. The more distant the galaxy, the more its light was stretched, and so the faster it was receding. The universe was not static. It had been expanding ever since its birth, every galaxy drifting apart from every other as the space between them swelled. For a long time, astronomers assumed this expansion must be slowing down, gradually braked by the gravity of all the matter pulling back on itself. Then, in 1998, two teams measuring distant, exploding stars found the opposite, and it stunned them. The expansion is not slowing, it is speeding up. Some unknown force is pushing the universe apart faster and faster, overpowering gravity on the larger scales. We do not know what it is, so we simply call it dark energy. Dark energy is the deepest mystery in cosmology, and it is winning. It appears to be a property of empty space itself, a faint outward pressure built into every cubic meter of the vacuum, so that as space grows, there is more space to push, and the expansion accelerates. It makes up most of the energy of the entire universe, far more than all the matter, dark and visible, combined. The cosmos is dominated not by stars, not even by dark matter, but by this invisible pressure driving everything apart. For the question of leaving, dark energy changes everything beyond our local neighbourhood. The galaxies outside the local group are not just far away, they are receding and accelerating as they go, carried off by the swelling of space faster than any ship could ever follow. To reach a galaxy outside our bound group, you would have to cross a gap that is not only vast but widening every moment, growing faster than you could close it. Most of the universe is not merely distant, it is moving permanently out of reach. This is a different kind of wall than gravity. Gravity holds us in, binding us to the Milky Way and the local group. Dark energy shuts us out, sweeping the rest of the universe away beyond any hope of contact. Between them, the two forces define a small island. We are held within our bound group of galaxies and walled off from everything beyond it by an expansion that no speed can overcome. And this expansion does not merely set a fixed boundary. It is actively shrinking the reachable universe with every passing year, as more and more galaxies cross the threshold beyond which their light and any ship could never catch them. The region we could ever touch is closing in around us, slowly but without pause. To see how completely the door is closing, we have to look at how that horizon of the reachable tightens over time. It would be comforting to think that, given enough time, we could reach anywhere, that patience alone would open the universe. The accelerating expansion takes even that comfort away. Because distant galaxies are receding faster the farther off they are, there is a distance beyond which they are moving away faster than light, carried not by their own motion, but by the swelling of space itself. Past that line, no signal we send, no ship we launch, travelling at any speed up to light, can ever catch them. They are gone for good. This boundary is called the cosmic event horizon, and it marks the true edge of the reachable universe. Anything inside it we could in principle still reach if we left now and travelled near light speed. Anything beyond it is forever cut off, not because it is too far in a fixed sense, but because the space between us is growing too fast to cross. The horizon is not a wall in space. It is a limit on what causality itself can ever connect to us. The cruel part is that this horizon is shrinking in terms of what it contains. As the expansion accelerates, galaxies that are reachable today are steadily crossing the line into the unreachable, one by one, as the growing space carries them past the point of no return. Every year, a few more galaxies slip beyond the edge, their light still visible for ages to come, but their substance already lost to us, impossible to ever travel to. The pool of places we could ever go is slowly draining. Far in the future, this leads to a lonelier cosmos than we can easily imagine. As expansion continues, all the galaxies outside our own bound local group will eventually cross the horizon and vanish from reach, and in the deepest future, from sight as well. Astronomers living in that far era on some world in the merged Milkdrometer would look out and see only their own galaxy, with the rest of the universe having receded into darkness. The evidence of the wider cosmos will, in time, be carried away entirely, so even light speed, the universe's ultimate pace, cannot beat the expansion. This is the final and largest wall. Within our local group, gravity holds us tightly and demands speeds we cannot reach. Beyond it, dark energy sweeps everything away faster than light can follow, and shrinks the reachable region year by year. We are penned into our small bound island of galaxies, and that island is, on cosmic scales, all we will ever be able to touch. There is a strange clarity in knowing the true size of the field. The reachable universe is not endless. It is our own galaxy, and its few bound companions, the local group, and nothing more, with the door to everything else already swinging shut. Even a civilization far greater than ours, with engines beyond our dreams, would face this same fixed limit, written into the structure of space and the nature of dark energy. All of this, the deep wells of gravity, the punishing energies, the widening dark, presses toward one of the oldest and most haunting questions in science. If leaving is this hard for us, it must be just as hard for anyone else out there. And that difficulty may quietly answer a riddle that has puzzled us for generations, the strange and total silence of a universe that should, by rights, be full of voices. For as long as we have understood how vast the universe is, a quiet question has followed. There are hundreds of billions of stars in our galaxy alone, many with planets, and hundreds of billions of galaxies beyond. The universe is ancient, and there has been time many times over for life and intelligence to arise. So where is everyone? Why, in all our looking and listening, have we found no clear sign of any other civilization? This puzzle is called the Fermi paradox, after the physicist Enrico Fermi, who reportedly raised it over lunch with a simple question: where is everybody? The paradox has many proposed answers. Perhaps life is rare. Perhaps intelligence is rarer still. Perhaps civilizations destroy themselves or simply do not last. But everything we have walked through tonight offers a quieter, gentler answer, one that requires no catastrophe and no rarity. Perhaps the silence is simply the sound of distance, of how desperately hard it is for anyone, anywhere, to leave their own corner of space and reach across to another. Consider that every wall we have met would stand for any civilization, not just ours. The rocket equation is the same on every world. The energy needed to push mass near light speed is the same everywhere. Every star sits at the bottom of its own gravitational well. Every galaxy holds its stars with the same deep grip, and the same dark energy sweeps the wider universe out of reach for everyone alike. The difficulty of leaving is not a human limitation. It is written into the physics that every species on every planet must obey. Seen this way, the great silence is not so strange. It may be that the galaxy is dotted with life, even with thinking beings, each one held in place by the very same walls that hold us, each looking up at the same impossible distances, each unable to cross the gulf to the others. Not destroyed, not absent, just bound, the way we are bound, to a single star and a single small region of a single galaxy. Civilizations might be common and still never meet. separated by distances that physics will not let them close. There is a sober comfort in this reading, and a loneliness too. It means we may not be alone in any final sense, that the universe could be alive with others. But it also means that the same laws keeping us home are keeping everyone home, that the night sky may be full of neighbours we can never visit, and who can never visit us. The silence would not be emptiness. It would be the quiet of a universe where everyone is held fast in their own place, calling out across a gap too wide for any voice to cross. This turns the Fermi paradox from a frightening riddle into something almost peaceful. The absence of visitors may not mean we are alone, nor that others have perished. It may simply confirm what this whole journey has shown, that leaving is the hardest thing in the universe, perhaps too hard for anyone. The stars keep their distance, and so it seems does everyone among them. If crossing to others is beyond us, the honest question becomes what we actually can do with the real tools we have and might yet build. The answer is smaller than the dream of leaving, but it is not nothing, and it is genuinely within reach. We can still send our machines, if not ourselves, out into the dark. After all the walls, it would be easy to end in despair, to conclude that the cosmos is simply closed to us. But that is not the honest conclusion. The truthful picture is narrower than the old dream of conquering the stars, yet it still holds real and remarkable possibilities. We may never leave the galaxy, or even reach another star in person. But our reach, through the machines we build, extends genuinely outward, and it is still growing. Start with what robotic probes can do that crews cannot. A machine needs no air, no water, no food, no return trip. It does not age in any way that matters, and it does not mind a journey of decades or centuries. The Voyagers are doing this right now, sailing into interstellar space, still sending back faint whispers of data after almost 50 years. They will drift on for millions of years, silent eventually but moving, our first real emissaries beyond the sun's domain. The next step is already being designed. Breakthrough Starshot, with its laser-pushed chips, aims to send tiny probes to Proxima Centauri within decades, fast enough to arrive in a single human lifetime and beam back the first close images of a planet around another star. These would be real visits to another sun, not by people, but by instruments small enough to push to a fifth of light speed. If it works, we would see the surface of another world circling another star, sent home as a signal across 4 light years. Closer to home, the possibilities are richer still. Within our own solar system, we can go almost anywhere, given will and time. We have landed machines on Mars, on Saturn's moon Titan, on a comet. We have flown past Pluto and out through the Oort cloud's near edge. Crewed missions to Mars are being planned in earnest. The whole solar system, that vast sphere of the sun's domain nearly 2 light years across, is genuinely open to us. A frontier large enough to occupy our species for ages without ever leaving the sun behind. This is the honest edge of the possible, not the galaxy, not even, for now, the nearest star in person, but a steadily expanding reach of robotic explorers, a thriving presence across our own solar system, and perhaps one day tiny probes drifting to the closest suns. It is a smaller map than the science fiction of starships and galactic empires, but it is real, grounded in physics we understand and already partly underway. The dream shrinks to fit the truth, and what remains is still extraordinary. There is dignity in knowing the true shape of what we can do. We are not going to escape the Milky Way. We are almost certainly not going to walk on a world around another star in any lifetime now imaginable. But we can know this galaxy intimately, send our machines across its nearest reaches, and read the light of its farthest stars. We can understand the very walls that hold us, which is its own kind of freedom, the freedom of seeing clearly. And so, we come back to where we started, to the pale band of light overhead on a dark and quiet night. We have followed the reasons all the way down, through every wall of distance and gravity and energy and time. It is worth standing once more under that band, knowing what we now know, and asking what it means to be held so gently and so completely by the galaxy that made us. Go back outside on that same moonless night and look up again at the pale band stretched across the sky. It looks exactly as it did at the start, a soft river of light, close enough to touch. But you see it differently now. You know that the band is the edge-on disk of our galaxy, 100,000 light-years of star seen from within. You know it holds us with a grip far stronger than its quiet glow suggests. We have followed the reasons all the way down. The nearest star is 40 trillion kilometers away, and our fastest ship would take 70,000 years to reach it. The rocket equation forbids carrying enough fuel. The energy to go fast climbs with the square of speed into figures beyond our power. The galaxy itself is a deep well, demanding hundreds of kilometers a second to escape. Most of its grip sourced from dark matter we cannot see, and beyond our small bound group, dark energy sweeps the rest of the universe away faster than light can follow. The honest answer to tonight's question is that we are held, and likely always will be, not by any single wall, but by all of them together, layered one inside the next, from the pull of the earth at our feet to the accelerating expansion at the edge of everything. The galaxy does not keep us with a fence we might climb. It keeps us with the deep structure of space and time, with the same laws that lit the stars and set them so far apart. There is no despair in this, only a kind of clarity. We are bound to the Milky Way the way a child is bound to the house they're born in, not as a prison, but as a home whose true size we are only beginning to grasp. It is an enormous home, a wheel of hundreds of billions of suns, with worlds beyond counting, and a whole solar system of our own still mostly unexplored. We have barely stepped into the yard, and perhaps the most beautiful part is the seeing itself. We cannot leave the galaxy, but we can understand it. We can measure the speed it would take to escape, weigh the unseen mass that holds us, trace the path of a star flung from the center, and read the stretched light of galaxies fleeing beyond reach. From one small rocky world on one quiet arm, a species learned the shape of the whole wheel it rides and the exact reasons it cannot leave. That knowing is its own kind of voyage, one we've already made. So we stay and we look up. The band of light that our ancestors called a road of milk turns slowly overhead, as it has for all the ages of the earth and will for ages more. We are part of it, made of its dust, lit by one of its stars, held in its long, slow turning. The Milky Way is not a barrier between us and somewhere better. It is the place we belong, vast beyond crossing and ours to understand. On a clear night, far from any city, you can still look up and see that pale band of light. Now you know what it is and why it holds you, and there is a quiet wonder in that, in being held so completely by something so beautiful, in calling a galaxy home.